Okay, guys, in this presentation we will talk about the reinforcement learning problem in terms of the main elements like states, actions, uh, reward functions, policy functions. So we will present all these concepts mathematically speaking, and we will discuss some others like value functions, the Bellman equations that are very important to solve reinforcement learning problems. And also we will discuss what algorithms are applicable and what are untractable, basically, and the way we can apply these algorithms in real problems. So we will talk about some theoretical concepts. In general, we talk about an agent and an environment. So the agent is always performing actions on the environment, and the environment responds to the agent given the next state, like changing and given the next state of the environment, and given a reward. A reward, remember, that is the reward will come from a function, a reward function, and the reward function is designed by the programmer. Okay. What we can modify about the action and the state is how the agent can perceive the state. If the agent perceives the state like with low level information or with high level information, and also with respect to the action, if the action that the agent will perform is going to be a high level action or is going to be a low level action. That's all we can modify with respect of the action and the states. But the reward, we can give the shape of the reward that we want. Since the reward function is going to be the only way we are going to let know the agent our goal, what is the goal in the problem. So we will always consider that the agent and the environment will interact at discrete time steps from 0, 1, 2. So we will always consider the time step t. The agent observes a state at some time step t. Okay, and this state perceived in time t, st, will belong to a set of states. This set of states could be finite or could be infinite. Once the agent is in some state, it will select an action to be performed, and this action could be this action will be noted as AT, and will belong to a set of actions that in this case we are defining this set of actions as a function of the state. So with this definition we are saying that the set of available actions for the agent will change depending on the current state. So this is a very general way to define the set of actions. You can also define this set as being only one set, like in the case of the state, we say this is a set of states and that's it. Or you can define it to be a function of the state, of the current state. Then after executing the action, the agent will perceive a reward in time step t plus 1. So the agent perceives the state in time t, perform the action in time t, and it will observe the reward in the next time step t plus 1. And the reward, we are saying here that is going to be a real number. And after receiving the reward, the agent will perceive the next state. So the environment is going to transition to a next state, s t plus 1, and the agent will perceive this to again select an action, perform the action, get a reward, and move to another state. So in general, we always visualize a learning process, a reinforcement learning process, as a transition from one state to the other. by the execution of an action and the observation of a reward. Okay, so we are in state ST, apply action AT, we get a reward in time step t+1 and transition to the next state ST+1 and so on. The agent is going to learn a policy. A policy is a function. A policy in time step t, we can write that as pi t, is a mapping from states to action probabilities. So in the most general form, we will define the policy function as a probability function, and we will use the letter pi to refer to this policy function. So this function here, the pi of SA in time step t, represents the probability that the action selected to be performed in time step t is A, and the current state or the state in time step t is some state S. And a well-defined policy will define or give a probability to every combination of state and action of our environment. So reinforcement learning methods specify how the agent changes its policy as a result of experience. So initially you can consider that this probability could be a uniform probability, an equiprobable probability. So you can give the same probability to any combination of state and action, because maybe initially we don't have any information about what states are good, what states are bad, or which actions are good depending on the state or not. So we can give the same probability initially, but as the agent starts its interaction with the environment, the agent will start applying learning rules and it will start modifying these probabilities. That's why we say that the agent will change its policy as a result of its experience. And we have said before that the agent's goal, roughly speaking, is to get as much reward as it can over the long run. So that's the way we are going to define our reinforcement learning problem, around the maximization of some reward. Now let's say something about the actions and states and the time, also about the reward and the environment. So many of these concepts in the end are or depend on the design decisions of the programmer. Like for example, the time steps does not necessarily mean that you need to keep track of some clock and say, for example, one time step will be of 5 minutes or 5 seconds. It could depend on the problem. Like for example, maybe a time step would be just making reference to the next play in a chess game, for example. So you will move or increase the time step every time a player makes a move. But at the same time, if you are, for example, programming a reinforcement learning agent for controlling a robotic arm, then maybe it is useful in that domain to consider time steps like really a specific number of seconds or minutes, but it does not necessarily has to do with specific fixed times of time, interval of times. In the same way, actions can be, as I said before, can be low level, like for example handling voltages, how much voltage you are going to give to any of the motors in the robot, or it can be very high level concepts, like for example go left, go right, or go home, move forward, move backward. It doesn't mean that you don't have to solve this, but it means that at the level of the reinforcement learning problem, you will have these actions available to the agent at the level of go home, for example, at the level of go right. Maybe go right will involve the use of other algorithms more complicated to calculate how much voltages you need to give to the corresponding motors to get the result of going right or going left. But this is something in terms of the reinforcement learning problem, this is something that the programmer will need to define. And the same way you can define the states in a different level of abstraction. Like suppose that you have a robot or a system that perceives from the environment using a camera or a system of cameras, and maybe the design of this reinforcement learning agent is based on the images that the cameras are perceiving. So the states could be like each of the frames of the camera. We're talking about a matrix of pixels. So this is like very low level information that will represent the state for an agent. Or it could be like very high level information, like for example, is the camera currently perceiving a person in front of me? So this concept of person would be solved by another program or another algorithm. So it depends on the problem of how you can implement the problem. Of course, as you increase the number of actions and the number of states that your agent needs to work with, you are increasing the complexity of the learning problem. An RL agent is not like a whole animal of robot, which consists of many RL agents as well as other components. So this idea of the RL agent as a whole animal is very difficult to accomplish. You will see when you implement these algorithms, you need to specify as clear as possible the goal that you want the agent to learn. So a system such complicated as an animal or a whole robot would need to be implemented using several reinforcement learning agents. So systems this complicated would be basically impossible to solve using only one reinforcement learning problem. You need to define several of them in different levels of abstraction. Another important point to consider when you are designing a reinforcement learning agent or algorithm is that the environment is not necessarily unknown to the agent, but it could be that simply the agent cannot control the environment, or at least completely control the environment. Like for example, if we were to design a robot for space exploration in a planet, of course the robot cannot, we cannot know what the agent will be discovering in that different in that application, different scenarios, of course. But if we were to develop a reinforcement learning agent to play chess, the agent can very clearly observe the board of the game, but it doesn't mean that it is easy to find or select the best next action to perform. The environment could be perfectly observable, but even in those situations, these problems are challenging. And with respect to reward computations, we would consider that this reward is the only information the agent will have to learn to improve the selection of the actions, and we consider this reward as part of the environment. And to consider this as part of the environment means that the agent cannot modify the reward function. In the environment, the agent can perform actions and make changes on the environment, but the function cannot be changed. Talking about goals and rewards, maybe the reward as a number is not like the best way to represent a reward, but it is very practical, and it allows us to define different algorithms based on this signal. Like maybe you can think of better ways to represent what the agent is perceiving as a reward, as a, I don't know, like a state where the agent is happy or is sad, or it's like overwhelmed with a lot of information. So maybe just a number is not enough. I mean, it's not like the best way to summarize all the perceptions of the robot, but it is a very practical way, and it works with the current algorithms that we have. And a goal should specify what we want to achieve, not how we want to achieve. So the goal should be a signal, a number saying, okay, this is a state that is very good, so I'm giving you a large number, a large reward, but I'm not going to tell you how you should arrive to this state. That's your task. That's what the agent needs to learn. A goal must be outside the agent's direct control, thus outside the agent. So this is the same case of the reward function. The agent cannot change the goals. The goals are given by the programmer. And the agent must be able to measure success. So we should define, for example, the states, how the agent perceives the states, in such a way that the state representation contains enough information for the agent to know if it is making progress, it is getting to the goal explicitly. And also, depending on how we define the reward functions, maybe the agent should be able to measure this success through frequently given rewards during its lifespan. So the agent should have information in the way it perceives the state to understand, to learn that it is making progress or not. Returns. The return, in few words, is just the sum of the rewards that the agent gains. So we have been talking about rewards, like in this case, a reward obtained in time step t+1, the reward in time step t+2, and so on. And what we want to do, or we want our agent to do, is to maximize these amounts of rewards. In general, we want to maximize the expected return. We will write this as the expected return, like big R, for each step t. Now I want to mention something. In the book, in the new edition of the book, the second edition, the return is denoted by the letter G, a big G. But it's the same concept, it's the expected return. In reinforcement learning, we will consider episodic tasks and continuous tasks. In the case of episodic task, we are talking about problems in which the interaction of the agent with the environment breaks naturally into episodes, like, for example, plays of a game, like imagine playing chess, or for example trips through a maze. And what we want to maximize here is the expected return, which is the sum of the rewards that you will get starting in the time step t. And if you notice here, you have to sum these rewards until some big T, which this big T may make reference to a final time step. So maybe here you can define this after 100 iterations or 1000 iterations, then the task will be considered over. And you can train or let your agent train during many episodes. So you can reinitialize the system and let the agent learn again until it reaches the time step big T. So this T is the final time step at which a terminal state is reached, ending an episode. So in an episodic task, we can give value to this big T, and we know that the expected return can be calculated by summing all the rewards from the current time T up to this final time step. If we are considering a problem with continuing tasks, so in this kind of task, it is not like easy to say an episode have ended here or not. And in this kind of situations, basically we are talking about a system that can work non-stop, so it can keep performing actions until infinity. So if we are talking about this kind of tasks, the expected return definition should be changed. In this case, we are adding this gamma value, which is, if you notice here, you will have gamma to the power of 1. In the next term will be gamma to the power of 2. Here, if we have a next term, will be gamma to the power of 3, and so on, where gamma is a value between 0 and 1. So the idea of this gamma is that we will discount the values of the rewards to make sure that if we compute the sum from some time step k equals 0 to infinity, as given in a continuing task problem, if we sum this to infinity, this sum will be bounded. So we won't end getting an infinite here. So that's why we need to reduce the rewards that we get more in the future. That's why we say that if gamma is 0, we are talking about a short-sighted agent. So we are talking about an agent that only sees importance in the more recently obtained rewards. Remember that T represents the current state. So reward in time step T plus 1 refers to the reward in the next time step, then in the next iteration. The reward in time step T plus 2 makes reference to the reward that you will get in this two more interactions. This reward here will be in 3 more interactions, and so forth. So if you consider gamma to be 0, so you're simply deleting the rewards, or you are not considering the rewards more in the future. So you are short-sighted, you are just interested in the next reward. But on the other hand, if you consider a gamma to be 1, then you are considering the rewards like in the episodic task. So you are considering the whole reward that you will get in time step T plus 2, T plus 3, and so on. So in this case, if you are going to work with the idea of a task that will perform an infinite number of times, then you should not select gamma or assign a value to gamma that is 1. It should be less than 1. And this, when we start considering this gamma on the value, is when we start considering the theoretical perspective. Remember that these definitions are developed from a mathematical perspective. How we can, for example, how we can bound this sum. In a practical problem, we know, of course, that we cannot let an algorithm run to infinity. So this concept is not that important in practical applications, but it is very important in the general mathematical framework, especially to be able to prove if an algorithm is going to converge or not. We need to consider the whole mathematical problem.